All right, welcome to This Explainer. Today, we're diving deep into the incredible science, the frankly mind-bending extremes, and the monumental engineering behind ITER. Basically, it's a $22 billion artificial sun that's currently being built right in the south of France. We're going to look really closely at the physical hurdles and the massive international cooperation needed to pull off what is, honestly, probably the most ambitious science experiment in human history.
So let's jump right into this enormous undertaking. I mean, we're talking about an unprecedented global attempt to capture the literal power that fuels the stars and then use it to solve our own energy crisis right here on Earth. Now, for decades, the idea of a self-sustaining fusion reactor has been the absolute holy grail of clean energy. But as you'll see, dragging the power of the cosmos down into a terrestrial facility, yeah, it's pretty much like trying to catch lightning in a bottle. Okay, here's our quick roadmap for today's explainer. We've got the holy grail of energy, mastering the fourth state, the magnetic containment web, balancing fire and ice, and we'll wrap up with a global bridge to tomorrow. Starting off with Section 1, the holy grail of energy, or basically why humanity is so obsessed with chasing a star in a bottle. Look, the big question is why? Why are we spending billions on this specific reactor? Well, it boils down to this. A self-sustaining fusion reaction is the ultimate clean energy solution. If we get the conditions right, controlled fusion releases literally millions of times more energy than burning fossil fuels. And it's even 4 times more energetic than the fission reactions we use in traditional nuclear plants today. But honestly, the real game changer is what it doesn't do. There's absolutely zero risk of a reactor meltdown, no long-lasting radioactive waste, and zero carbon emissions pumped into the atmosphere. It's kind of the perfect energy source, provided we can actually build a machine capable of housing it. Which brings us to Section 2, mastering the fourth state. This is all about the chaotic science of catching that lightning and how it all builds on the fundamental physics of matter. So, to really grasp fusion, we first need to talk about plasma. We all know solids, liquids, and gases, right? Well, plasma is the fourth state of matter. It happens when a substance gets so incredibly hot that the center of an atom actually completely separates from its electrons. I absolutely love this description from the source material. They call plasma a very spicy soup of free electrons with charged ions moving through it. And because it's full of all these charged hyper-energetic particles, plasma is just wild. It's chaotic. It is incredibly difficult to contain. I mean, you can't just stick it in a normal metal box. It would instantly melt right through it, or it would just rapidly cool down and completely ruin the reaction. Now, what's really fascinating here is just how beautifully simple the core reaction looks on paper. ITER uses a very specific fuel mix, deuterium and tritium, which honestly are just fancy names for hydrogen atoms carrying 1 or 2 extra neutrons. When extreme heat forces these particles to overcome their natural repulsion and finally fuse together, they produce just 2 things, totally harmless helium and a spare, highly energetic neutron. And that high-energy neutron, that is the vehicle carrying the massive heat that we ultimately want to capture to generate actual power. But here's the catch, and it's a massive one. We call ITER an artificial sun, but the real sun has a huge advantage over us, immense, crushing gravity. That gravity naturally bears down on all those particles in the sun's core, jacking up the density so much that fusion can happen at relatively lower temperatures. ITER doesn't have the mass of a star. In fact, it's operating with less than a single gram of fuel inside its massive vacuum chamber at any given time. So because it lacks that extreme density, it has to compensate with extreme heat. To force that tiny speck of fuel to fuse here on Earth, the plasma inside ITER has to be heated to temperatures more than 10 times hotter than the core of our actual sun. All right, that leads us perfectly into Section 3, the magnetic containment web. How on earth do you control the uncontrollable? Well, since the plasma is so impossibly hot, literally no physical material on Earth could hold it. The only way to effectively bottle a star is by building a cage made entirely out of magnetic fields. So to trap that wild plasma, ITER is building the largest magnet in the world. Once it's fully assembled, the central solenoid magnet alone is going to be 5 stories tall and weigh a massive 1,000 tons. This absolute behemoth sits right at the heart of the reactor, playing a crucial scientific role in starting and maintaining those fusion reactions inside the donut-shaped chamber, which we call a tokamak. But it's not just about brute strength or massive size, right? It is about mind-blowing precision. The source material puts this so beautifully. To contain those microscopic particles, the magnetic weave has to be like high thread count Egyptian cotton. It has to be super, super tight. even though they're building a machine 10 times bigger than any previous reactor. Using these massive D-shaped and circular magnets all around the chamber, the precision still has to be measured in millimeters. One tiny imperfection in the magnetic field and poof, that spicy soup of plasma escapes. And building this massive, millimeter-perfect magnetic web, yeah, that is not a solo mission. It relies on a sprawling global supply chain. Because the partner nations are contributing components instead of just handing over cash, everything is measured by value. Europe leads the pack at 45%, while the US, China, Russia, and a few others each handle vital 9% chunks, manufacturing these highly specific magnets and vacuum chamber slices all across the globe. They use a consensus decision-making model to manage this incredible choreography of scientists and engineers pooling their resources. It is just a stunning display of international collaboration, all working toward a shared vision of a better future. Moving right along to Section 4, Balancing Fire and Ice. Let's look at the ultimate thermodynamic tightrope that makes building this machine so wildly challenging. Inside the ITER Tokamak, the plasma is going to reach a staggering 150 million degrees Celsius. Just let that sink in for a second. Once it ignites, the interior of this reactor literally becomes one of the absolute hottest places in the entire solar system. Yet, right next to that raging inferno is the exact opposite extreme. Remember those massive 1,000-ton superconducting magnets we just talked about? Well, they only work if they are kept extremely cold. We're talking just a few degrees above absolute zero. If they warm up even a little bit, they lose their superconductivity. The magnetic cage completely fails and the plasma gets out. So you've got one of the hottest environments imaginable sitting directly next to one of the coldest environments possible. And what separates them? A delicate, ultra-thin heat shield. Talk about an engineering tightrope. And this is actually where ITER recently ran into a massive wall. They discovered these tiny, millimeter-sized leaks in the heat shield's cooling pipes. The fallout? They had to rip out roughly 20 kilometers of piping just to refabricate the shields. It was a staggering setback, costing the project an estimated 5 billion extra euros. It just goes to show, when you are pushing the absolute extreme boundaries of physics, tiny flaws create incredibly expensive realities.
Which brings us to our final section, a global bridge to tomorrow. This is how we are paving the way for commercial clean energy.
Now, earlier we mentioned the fuel mix, deuterium and tritium. Deuterium is super abundant in nature, but tritium? That is very, very scarce. So how do you run a global power grid on a fuel that barely even exists? Well, remember those spare high-energy neutrons produced in the fusion reaction? Because they don't have an electrical charge, they aren't trapped by that magnetic cage, so they fly outward and slam right into the walls of the Tokamak. Well, ITER is testing a brilliant superpower to solve the fuel problem. They are lining specific wall shield blocks with lithium. When those flying neutrons smash into the lithium, it will literally breed more tritium right there inside the reactor. If they can demonstrate this at scale, future fusion reactors will actually manufacture their own rare fuel while they run. How cool is that?
And this specific fuel breeding test really highlights ITR's true purpose. ITR is a research tokamak. It is never going to provide power to the electric grid. But honestly, that was never its job. Its job is to serve as an open book for researchers all over the world. They are actively writing an engineering handbook that details every single mistake they make and everything they learn. They're even developing open-source software to predict plasma behavior for anyone to use. So really, ITR acts as a bridge. Every agonizing multi-billion-dollar problem that ITR solves right now is one less problem that private commercial fusion startups will have to confront when they build the actual power plants of tomorrow.
So after years of setbacks and massive budget increases, ITER is currently targeting 2034 for its first plasma ignition. Now, for decades, the running joke has always been that fusion energy is always a decade away. But when you look at the sheer scale of the science, the unprecedented international cooperation, and the very real physical infrastructure being meticulously woven together in France right now, we might finally be living in the very last decade where this world-changing technology is treated as just a distant dream. So I'll leave you with this thought. As this massive artificial sun gets ready to wake up and bridge the gap to commercial clean energy, how do you think unlimited, carbon-free fusion power will reshape the future of our civilization? Think about that and keep exploring.